So in this video, we're going to be talking about Lewis dot structures, and we've talked about Lewis dot structures before in the atomic theory unit when we were referring to individual atoms. So just as a quick review, if we have sodium, boron, fluorine, and argon, we know that sodium is in column 1 in the alkali metals, and so that means it has one valence electron, so we would put one dot. Each dot represents one of its valence electrons. Boron is in column 13 in the boron family, and it has 3 valence electrons. Now, when we have more than one valence electron, we always make sure to put an electron on each side. Now, I always start at the top and work clockwise, but you could also do something like this or like this, and all would be equally valid answers. However, it would be incorrect to write boron like this. That would be wrong. Okay, so we don't want to look at that. Fluorine is in the halogen family, column 17, so it has 7 valence electrons. So I put 1 on each side, and then add the rest, so we have 7. And then argon is in the noble gases and has 8 valence electrons. Okay, so Lewis structures are the way that we draw compounds to show that they have reached the octet. So I have the the steps listed here. But one of the best ways to really do this is to actually just practice and see it happening. So first thing we're going to look at is hydrochloric acid, HCl. So chlorine has an electronegativity value of 3.0. Hydrogen is 2.1. So when we subtract these, we get 0.9. Now, when we have a value of 0.9 as our electronegativity difference, we know that that will make us a polar covalent molecule. And so we have, first thing we need to do in terms of actually drawing the structure according to our steps is count the number of valence electrons in the element / compound. Okay, and so when we do that, we know that we have hydrogen and chlorine. Now our one hydrogen is going to donate 1 valence electron because it's in column 1. Chlorine can donate 7, so altogether we have 8. Now this becomes my quote-unquote bank of electrons that will participate in bonding. You can think of drawing a Lewis structure as building a house, but instead of building a house, you're building a compound. And the bank of electrons is the money that you have to withdraw in order to get the materials to build your house. So it says the first element is listed. It should say that is listed. Good job, Miss Nichols, with your typing. Is listed is usually the central atom. Now it says usually. That means there are exceptions. The big exceptions are if it starts with H. Hydrogen is never a central atom. So you draw that first and connect the other atoms around it. Now in this case, we only have 2 atoms. We just draw hydrogen and chlorine, and we draw a single bond connecting them. Okay. Now, we know that each bond or each dash represents a bond containing 2 electrons. Okay, so we would subtract these 2 electrons that we used from our bank. So we have 8 electrons minus those 2, so now I have 6. And we've done steps 1, 2, 3, and 4. So now we want to talk about we want to count each electrons connected to the element, and they have to meet the octet rule. The exceptions are hydrogen. Surprise, surprise with hydrogen. It's okay with just 2 valence electrons. And boron is okay with 6 valence electrons. Okay, now if I can get this to, there we go, 6 valence electrons, which would be 3 single bonds, and hydrogen would be 1 single bond. So we check the octet. Hydrogen has the 2 bonds, or the 2 electrons in the single bond, so it is satisfied. Now chlorine only has 2. It needs 8. So that means it needs 6 more. Well, look at this. We have 6 in our bank here. So if I take the 6 electrons and I put them as lone pairs around the chlorine, that uses up all the electrons in my bank, and now both hydrogen and chlorine are satisfied with their octet. If we do the same thing with carbon and hydrogen, we know that we have, you can calculate the electronegativity difference and intermolecular forces on your own, but if we're just counting up valence electrons, we know that we have 4 valence electrons that come from carbon, and we have 4 hydrogens, so that will give us a total of 4. And altogether we have 8 valence electrons in our bank that are going to participate in bonding. So remember, that first atom listed is always going to be your central atom unless it's hydrogen. And so we're going to put carbon in the center and connect hydrogen around it. And we know that we have 4 hydrogens because of this subscript here. And so we count, well, first we take our bank, we subtract the ones I used. 1, 2, 3, 4, 5, 6, 7, 8. So I have 0 electrons left in my bank. And if I look, hydrogen all has 2 electrons that are being shared, so it's happy. And carbon has a total of 8 with its 4 single bonds, so it is also satisfied. Water, on the other hand, let's look at water. We have 2 hydrogens, which are going to donate 2 electrons, and we have oxygen, which is going to donate 6. So, again, normally the first atom listed is your central atom. However, hydrogen is the exception. So we're going to put oxygen in the center and connect our 2 hydrogens to it. Oh, and we have a total of 8. And we subtract those 4 that we used there. So we have 4 left. And if we look, we see that hydrogen is satisfied with its 2 electrons, so it doesn't want any more bonds. But oxygen right now only has 4. It needs 8. Well, there are 4 left in the bank. And so we can draw it as having 2 lone pairs around it, which would give us 0. Now, usually we would draw these to where the lone pairs are on opposite sides of the oxygen to demonstrate that they are far away. If we look at the actual 3-dimensional shape, you would see that water actually has a more bent shape to it. It's not completely linear and would look actually more something like that. But this first way of drawing it is perfectly correct for our class, especially because we have not talked about 3-dimensional geometry of molecules. If we look at oxygen, okay, so number 4, oxygen, we have 2 of them, and they each have 6, so that means we're donating 12. Now notice this is the first time that it is not 8. If it's in multiples of 8, you can be pretty confident in your single bond status. However, when you deviate from multiples of 8, you're most likely going to have a double or triple bond in there somewhere. So if we look at oxygen, we only have 2 molecules. So if we draw it this way, and I hope you're using a pencil, because I'm about to show you something, and then you're going to have to erase some stuff. So if we have our 12 electrons, and we subtract these 2, we have 10 remaining. Now, we both know that they each need 6 valence electrons. So if we do that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, if we subtract 12, that gives us a -2. That -2 tells me that I need to add a double bond in there somewhere. So instead of having a single bond, we need to get rid of 2 of our lone pairs and make it a double bond instead. And that would give us we would add those 2 electrons back to get 0, and it would give us our double bond. Okay. So That's kind of the intro to it. You should come see me if you need help with these other ones. One quick thing about sodium chloride is we know that sodium chloride is going to be ionic. So if you have an ionic bond, we know that sodium and chlorine, they're going to transfer their electrons. So sodium will have a positive charge, this whole thing overall, and no valence electrons, excuse me, whereas chlorine will have received its 8th valence electron from sodium and will overall have a negative charge. And that's kind of how we would draw that there. And then in the next problems, we have in number 11 and number 12, we see that there is an overall charge to the molecule. So this means we would add 2 additional electrons to the bank. So for example, carbon we know has 4. 3 oxygens would give us 6, 12, 18, plus the 2 valence electrons would give us a total of 24 in our bank in order to do this. Okay, CO3 is a polyatomic ion, and one of the reasons why it exists as an ion is because this compound cannot exist without those extra 2 electrons in order to satisfy the octet for both the 3 carbons and, excuse me, the 3 oxygens and the 1 carbon. So if you have any questions about that, come see me in class.